Welcome back. Here we shall derive the formulas for calculating the area moment of inertia of some standard cross-section shapes of a beam about the respective centroidal or neutral axis. In the last lecture, we derived the flexure formula where the area moment of inertia about the neutral axis was defined as one of the parameters. In this lecture, we shall understand why the area moment of inertia plays a very important role in the bending theory and shall also derive standard formulas for basic planar sections about the neutral axis. The neutral axis coincides with the centroidal axis for initially straight beams, and it separates the cross-section area into two distinct zones, one with tensile bending stresses acting on the longitudinal fibers and the other with compressive bending stresses. The neutral axis or neutral surface in particular does not bear any bending normal stress but only deforms its shape from initially straight to a circular arc in the presence of maximum bending moment. Let's look at the flexure formula in part defined by m over I equals sigma b over y. Intentionally, b is used as subscript to denote the normal stress on an elemental fiber due to bending or simply bending stress. M is the maximum bending moment at some section along the beam's length. Y is the distance of the cross-section area of the elemental fiber from the neutral axis. And as explained in the last lecture, I is the area moment of inertia of the beam cross-section, which is defined by the area integral of second moment of differential area about the neutral axis. The unit is found to be millimeter to the power of 4 or meter to the power of 4. Looking at the formula, it is evident that more is the value of I for a beam cross-section, the lower is the induced bending stress for a given maximum bending moment. Rearranging the terms, the bending stress can also be written as m over z, where z is given by I over y and is known as the section modulus, with units of millimeter to the power of 3 or meter to the power of 3. More the value of I and hence z, lower is the value of the induced bending stress. Hence, I signifies resistance to bending deformation, and for a given bending moment and for a given shape of the cross section, a higher value of I should always be strived for. A simple bending test may be conducted on a steel ruler having rectangular cross section using both the hands as the supports and inducing bending moment on the ruler. It is found that the ruler is easy to bend if the bending is about the x-axis axis, while it is very difficult or rather impossible for us to bend the ruler if we rotate it by 90 degrees about the longitudinal axis, so that bending is now about the y-y axis. As you shall see shortly, it is found that the area moment of inertia about the y-y axis is much higher than the area moment of inertia about the x-axis axis, hence the difficulty in bending about the y-y axis. All the beams used in the construction industry and in machines other than the circular cross-section ones have their depth values larger than their widths for the same reason. A word of caution. Note that there is another moment of inertia that we encounter in mechanical studies, which is defined specifically as the mass moment of inertia, the unit of which is kilogram meter square and signifies resistance to rotational motion due to the inertia effects. While the area moment of inertia is related to statics and the area properties of the beam cross-section, the mass moment of inertia is related to dynamics and the mass properties of the whole body. The same symbol, that is capital I, is used for both these types in many text and reference books though. Now that the significance of area moment of inertia is understood, let us now understand how to derive the area moment of inertia for some basic planar shapes. This will eventually help us to calculate the area moment of inertia for some complex shapes of the beam cross-section comprising these basic shapes. Let's begin by drawing a rectangular cross-section area with width b and depth d. Assuming that the beam is horizontal and the load is acting on the top of the beam, the neutral axis is the one about which bending takes place, and for initially straight beams it coincides with the x-axis here, passing through the centroid. Let's denote a thin horizontal rectangular strip of width b and depth del y at a distance y from the neutral axis. The area of this strip is del a, which is b times del y. Applying the definition of area moment of inertia to this strip and integrating it to cover the entire depth, I equals area integral of y squared times dA. With simple integration techniques, we get the value of I as b times d cube over 12. That is, the value of area moment of inertia for a rectangular section about an axis is parallel edge dimension times the cube of the perpendicular edge dimension over 12. In the same sense, it is easy to show that the area moment of inertia for the section about y-axis should be d times the cube of b over 12. It is important to note that I about y-axis should be used for the calculations only when it is expected that the bending is occurring about y-axis due to a horizontal load applied from the sides. As explained a while ago from the formulas, it is easy to note that here the beam is difficult to bend about the x-axis since I about x-axis is more than I about y-axis, signifying more resistance to bending. Let's now calculate the area moment of inertia for a circular cross-section. We show a circle of radius r units and a concentric elemental circular strip of thickness del r at a distance of r from the center. We denote the x-axis and y-axis passing through the center. To find either ixx or iyy for convenience, we first calculate the I about the perpendicular longitudinal axis zz, which we call as the polar axis, because it joins the poles at the ends of the cylindrical beam. Now, izz or ip, p for polar, equals area integral of r squared times differential area dA. dA equals the perimeter of the circular strip times the thickness. Eventually, we have the polar moment of inertia as pi over 32 times the diameter d to the power of 4. Now, using the perpendicular axis theorem, we have Iz equals Ix plus Iy, but Ix is equal to Iy due to symmetry. Hence, Ix or Iy equals pi over 64 times diameter d to the power of 4. Ix or Iy can be called as I about the diametral axis. Finally, let's calculate the area moment of inertia for a triangular section. Here, we take the reference as the apex of the triangle for convenience. For the differential area, we show a thin horizontal strip of thickness del y at a distance of y from the reference, that is the apex. The width of the strip as it proceeds from the apex to the base of the triangle increases linearly. For the differential area, we show a thin horizontal strip of thickness del y at a distance of y from the reference, that is the apex. The width of the strip as it proceeds from the apex to the base of the triangle increases linearly. For the arbitrary strip at distance y from the reference, the width b at y denoted by b suffix y is found from simple interpolation as y over d times b. The differential area del A of the strip is b at y times del y. Incorporating the definition of area moment of inertia about the horizontal axis passing through the apex and simplifying, we get the result as b times cube of d over 4. To find the area moment of inertia about the centroidal or neutral axis, which is parallel to the axis passing through the apex, we invoke the parallel axis or transfer axis theorem, which states that I about any other axis parallel to the neutral axis equals I about the centroidal or neutral axis plus the area of the triangle times the square of the distance between the two axes. Here the distance between the apex and the neutral axis or centroidal axis is 2/3 of the depth d. This distance can easily be derived from elementary calculus and is skipped in this lecture. Simplifying, we get the area moment of inertia about the neutral axis as b times the cube of d over 36. If the area moment of inertia about the axis passing through the base is required for some reason, the same principle, that is the parallel axis theorem, may be applied to get the result as b times the cube of d over 12, which is similar to the area moment of inertia formula for the case of a rectangular cross-section area about the neutral axis. Let us summarize the results obtained for the area moment of inertia for the three basic planar shapes for future reference. In the next lecture, we shall calculate the area moment of inertia of some complex beam cross-section shapes about the respective centroidal or neutral axis by first calculating the centroid of the complex section, followed by the addition of the moment of inertia of individual shapes with respect to the centroidal axis.